So let's talk now about hypothesis space. The idea here is we have some function which computes a y-hat. And this function is actually parameterized by our parameters theta. So you can really kind of think of it as twofold. The function includes both the input and then whatever the parameters are. So if we looked at something simple, let's say we looked at, for instance, x along with m and b for a line, right? So this would be mx plus b, which would be our y-hat. Our hypothesis space is the set of all possible functions as parameterized by theta. So for example, in this particular case, what we're looking at is all single-degree polynomials. So we have an infinite number of possible functions based on whatever pairs m and b that we have. But what we know, if we look at our function, is it's always going to be a line of some sort. Okay? That's all that we can produce. So our hypothesis space is a set of all possible functions. So we're looking at all possible theta given some structure of f. Because if we look at really f of x, as we look at this theta, this provides us now a universe of different possible f's. So for instance, we could have the f that consists, let's say, of an m of 3 and a b of 2. We can have an f that consists of -3, 7.6, and we have all these possibilities. So what we're doing is searching through our learning process, our gradient descent is searching through this space of all possible thetas, trying to come up with a good theta. But as you can see, the hypothesis space limits what you can represent. So this hypothesis space represents just single lines. If we wanted to look at 10-degree polynomials, for example, that is a different hypothesis space, right? So if we looked at 10-degree polynomials, then this is something that would give us of the form, let's just use summation notation. Summation notation from, let's say, I equals 0 to 10 of some theta sub I, x sub I, x to the I. So this is going to give us theta of 0 plus theta of 1x1 plus theta 2x2 all the way to theta 10 x to the 10. Here we've got a richer hypothesis space, right? We have, first off, more parameters. So instead of having 2 parameters over here, we actually have 10 parameters, and we can represent a lot more different functions. So we could represent, for instance, that function, and we could represent all sorts of other 10-degree polynomial functions. So that's great. We still are limited in the functions that we can represent. Let's say we've got a regression problem with some underlying data. And our data looks like something like this. We've got a bunch of data. And the question is, how well do we think a hypothesis space of linear functions is going to work to solve this regression problem, right, to give us low loss? And the answer is probably not too well, right? The best we can do is perhaps some line through here, but we'll get a lot of error here and a lot of error here. On the other hand, if we had a hypothesis space that was quadratics, then we're much more likely to get a line that fits this data better. So we'll have lower loss. So the first example would be a case of underfitting, where our hypothesis space is not rich enough to represent our data. Whereas if we had a quadratic, or certainly since 10-degree polynomials are a superset of quadratics, a 10-degree polynomial, we could map this much better. What about, on the other hand, let's say we have this, and here we've got temperature. Okay. So what we might expect is our temperature starts low and So if we take some samples, let's say, it starts low, and then it goes up, and then it comes back down. So we go up and down. So this is an example where a quadratic wouldn't fit quite as well as something like a sine function. We could look at a hypothesis space which includes sine functions. So we could look at something like, let's say, we could look at something like a sine of bx plus c plus d. So we would provide these 4 parameters, a, b, c, and d, and they would allow us to stretch the sine function both vertically and horizontally and shift it up or side to side. So for some sort of a problem like this, this might be a better hypothesis space to be using. When we begin to talk about neural networks, we're going to learn basically all neural networks really are matrix multiplies along with some nonlinearities. Okay? But it turns out that neural networks actually are universal function approximators. So they can actually, given enough parameters, approximate any sort of a function we might have. So they could approximate a quadratic, a polynomial, a sine function, any function really. So any set of data a neural network can approximate. So therefore, that's why we really like to use neural networks, is because the fact that the hypothesis space, assuming we have enough parameters, is going to be rich enough that we can represent the function that's going on with our underlying